Good afternoon, guys. We're moving on from learning about covalent bonding and the single, double, and triple bonds to learning about how those bonds give molecules shape and making some molecules polar and some nonpolar. And so, as always, covalent bonds are about sharing electrons between nonmetals. So today's goal is about the 6.3 section describing the shape of compounds, which is described by this Vsepr, which stands for valence shell electron pair repulsion. And so the valence shell, those electrons involved in bonding, pairs of electrons, they repel each other, and that gives them shape. Looking at the study design extract from here, here we're learning about the shape of molecules and an explanation of their polar or non-polar character with reference to the electronegativities of their atoms and electron pair repulsion theory. And so electronegativity, we learnt about it when we were learning about the periodic table. The trend was that the top right-hand corner was the most electronegative, had the strongest attraction for another electron. And so those elements like nitrogen, oxygen, and fluorine are the top three in electronegativity. So what you're going to be doing today, looking at the text, watching this video, answering these questions, and there's one here from the student workbook. So I'll let you read the text, but now I'm going to jump to this. So firstly, the shapes of molecules, or VSEPR. And so electron pairs repel each other in 3 dimensions. They're 3-dimensional objects, which will give you 4 things repelling each other, a tetrahedral shape. It's worth having it in the back of your mind. That's a 109.5 degree bond angle. That's as far apart as 4 things can get in 3 dimensions. And so the number of bonds decides the shape of a molecule, and it refers to a central atom. These are relatively simple examples here. And so the first example is where we've got 4 single bonds. All of these examples are shown something bonding with hydrogen, but it doesn't have to be hydrogen. This black atom here in the middle is carbon because it makes 4 single bonds. And you can see here that representation of the 4 things coming off it as far apart as they can, tetrahedral. If I've got 3 bonds, and so I've got 3 hydrogens here, I've got a lone pair up here which isn't shown. The shape that we get with this central atom is like a pyramid. And so surprisingly, or not surprisingly, we call it a pyramidal shape. And you might recognize that this one has to be nitrogen because it forms 3 single bonds. Next possibility, I can make 2 bonds, and I'd have 2 lone pairs not shown here, and that gives a V-shaped or bent shape. And the most important example of this one is water, because this red color is often used for oxygen, and yeah, water has that V-shaped or bent shape. And final possibility, 4, 3, 2, 1 single bond, and there's 3 lone pairs here, and that gives you a linear shape between these 2 atoms. And this one is actually hydrogen chloride. Green's often used for chlorine, and chlorine is actually a really important element for chemical synthesis. 2 other things not shown in this table. A double bond will make something planar, like flat, and a triple bond will make things linear. And so it'll be easier. I'll show them later. Now, what's next? couple of sample questions. Using the electron dot diagram or its valence structure, draw the shape diagram for a molecule of H2SE. There is in your text, which hopefully you're accessing electronically, these videos. And they're pretty good, so definitely give it a look.
In this question, we're being asked to draw the shape diagram for a molecule of H2SE.
Please watch it. Like it's nice and slow. Yeah, I think it'll make things much clearer for you. And there's 2 videos like that linked through your electronic text and a couple of things to practice problems which follow on. Next thing I want to talk about, bonds. Bonds can be polar or non-polar. How? They're going to be polar if they're between different elements. And because if they're different elements, the electrons will be pulled to the one which is more electronegative. And it's going to cause that element to be slightly negative, not full negative like an anion, but slightly negative. It's got a bigger share, a bigger share of the electrons. And we show this using the symbol delta negative. And so this symbol here is the lowercase delta, and this triangle here is uppercase delta that we use for things like change in temperature. So this one, delta negative slightly. And yeah, if there's 2 different elements, one of them will be slightly negative or more electronegative and give you that delta minus. And the one which is lower electronegativity will have be delta plus. And if that's the case, we say that the bond has a dipole, that the sharing is not even of charge. If I get that out of the way, hopefully you can see that. If it is the same element, then the electrons will be evenly shared and you'll have a non-polar bond. Check out the animations. So we have to be able to see, state which of the following bonds are polar or non-polar: oxygen to oxygen, hydrogen to phosphorus, oxygen to chlorine. And a key thing to help us do this is a table of electronegativity. We'll go here, sample. And this is shown here, the Pauling scale. Linus Pauling, who the scale is named after, was one of the most important chemists of the 20th century. Won the Nobel Prize twice, I think. And he developed a scale for ranking electronegativity. It's the most commonly used one. And you can see that like you'll need a table like this to work out which element is more electronegative in a bond. Back to this. Actually, this question is only about are they polar or non-polar. To show that you're listening, if they're different elements, they'll be polar. Next, and this is more important, we have to work out whether a molecule is polar. And it's important here to notice here we're talking about molecules and not lattices like when we were talking about metals and when we were talking about ionic compounds. And so in a lattice, lattices are continuous, and so there's strong bonds in all directions. But molecules are separate, they're discrete. And so the strong bonds, the covalent bonds are strong as a metallic bond, as strong as an ionic bond. But between the bonds, there's weak between the molecules, there's weak bonding, and we're going to spend time next week learning about those different types of weak bonding. But which type of weak bond it is depends on the polarity of the molecules, and that's why this is a key question. A molecule is polar if it's got two things. Number one, it's got polar bonds, and number two, the charge is asymmetric. Now, so again, a couple of examples here. For a molecule to be, you get pretty much the decision you have to look at it is look at the atoms involved, are the bonds polar, and if they are polar, is the charge unsymmetrical? Asymmetrical is the better word. So in water, pretty much it's not. You've got polar bonds, and it's not symmetrical. The oxygen at the top is the delta negative, and the two hydrogens down the bottom are the delta positive, and so you've got a negative end and a positive end of that molecule. And so water is a polar molecule, and that's so important to how water behaves. Now, I'm at almost 12 minutes. Questions 1 to 10, I'm only showing 1 to 5 here. They're the ones to do. Cool, I'll leave you with that and see you on Thursday.